Our next type of reaction are called the single displacement reactions. In these types of reactions, an element is going to react with a compound in such a way that a new element and a new compound are created. In these particular types of reactions, electrons are transferred from an element to a cation. Remember, cation are positive ions. The process of doing this means that the element that's doing the transferring will become a cation, and the cation that ends up picking up the electrons will become an element. So the general form looks like this. A, that's our element, plus B, C, that will be our compound, will form B plus A, C. So an example, sodium metal and magnesium chloride. So this is A, this is B. You notice what happens that A and B switch places. So that means that B becomes the free element, and now Na will bond to Cl. Now, it's important before we write the formula for Cl that we write the oxidation states for the compound quickly. Now you notice that this is Mg plus 2. Since it becomes an element, its oxidation number will go down to 0. That means that it actually picked up 2 electrons from sodium. Now sodium then will become an ion. Sodium will now become Na plus 1. Before it was an element, now it's sodium the ion. And now sodium will bond with chlorine. Chlorine is still -1. So you note that the formula for NaCl, there's no 2. The 2 here was because magnesium plus 2 was bonded with chlorine -1. Now remember, these are unbalanced chemical equations. So if we balanced it, then we would make sure that we have the right number of chlorines on both sides. Now, one important note for single displacement reactions. These are conditional. Well, what does that mean? It means that the element A must be more active than the cation B, or no reaction will occur. Okay, so how do you find out if element A is more active than the cation B? In order to do that, you need to use something that's called an activity series. Okay. On this page, this is a copy of the activity series that you should have. Now, there are two columns for the activity series. First thing I suggest, because it will get confusing a little bit later, is somewhere on your activity series you should write that these are for single displacement reactions. Now, the way the activity series works is, on the left-hand column is a way to compare metal to metal. The top of the column are the more active metals, and the bottom of the column are the less active metals. So when you're looking at your single displacement reaction, you're going to be looking and saying, okay, which one's element A and which one's element B? Then you're going to look up element A and element B on the activity series, and you're going to determine if element A is higher up, meaning it's more active than element B. Now, since you're going to be turning elements into cations, down here for the transition metals, it gives you the oxidation number to use if your metal ends up becoming a cation. You will also notice that there is a non-metal on the list. This is hydrogen. Okay, a hydrogen ion means it's going to be, if the hydrogen is the positive ion, that means that you're going to be looking at acids. Okay, a lot of times when we think about metals reacting with acids and eating them away, that's actually just a single displacement reaction. Okay, in that case, the metal is giving its electrons to the hydrogen in the acid. Okay, and in that case, what happens is it always produces hydrogen gas when metals are getting eaten away by an acid. Okay, we're going to come back to the halogen here in just a minute. So let's look at some examples of how do we actually use the activity series and predict the products of a single displacement reaction. Okay, when you have single displacement reactions, you will get that. That's all you get. You get the two reactants. You are going to have to decide if element A is more active than element B, and if it is, then they're going to switch places and you're going to write the formulas of the two new products. If element A is less active than element B, then you're going to write no reaction. Alright, so element A is going to be, this one's A. Element B is right here. It's actually in the cation state, so it's barium. So we're going to go back to our activity series and we're going to compare the position of potassium to the position of barium to determine if it looks like this reaction will actually occur. Okay, so let's go back to our activity series. Here's K, here's Ba. So K is metal A and Ba is metal B. So potassium is higher up than Ba, so potassium is more active. Okay, let's go back to our example problem. Okay, so K is more active than Ba, so that means that K is going to and Ba are going to switch places. Now, before we do that, I told you to write the oxidation numbers in your compound. Okay, if you look at your periodic table, barium is +2, sulfate is -2. Okay, so K and Ba are going to switch places. So Ba will now be alone. And now you're going to have K taking this position. And you'll have K bonding with SO4. Now the SO4 is still -2. And now the potassium is an ion. And if you look that up on the periodic table, when potassium is an ion, it's +1, meaning that the formula is 2. Okay, let's look at a couple more examples. Okay, Pb plus AgNO3. So lead will be our metal A, and silver will be our metal B. Let's go to the activity series and compare the positions of lead and silver. Okay, lead and silver are farther down. They're transition metals, which means they're not terribly active to start with. Okay, but here's Pb, and here's Ag. So Pb is going to be able to knock out Ag. It's going to be able to replace the Ag. That's why we call them single displacement or single replacement reactions. Okay, so that means that Pb is going to become an ion. It shows you right here that Pb, when it becomes an ion, will become Pb plus 2. Let's go back to our sample problem. Okay, Ag is always 1. Or, if you look at it very carefully, nitrate's always -1, and there's 1 silver and 1 nitrate. So Ag is going to be positive 1. Okay, now Pb is going to knock out Ag. So Ag, left out here. Pb will take NO3's place. Excuse me, Pb will take Ag's place and bond with the NO3. Okay, we just said that the activity series told us that Pb will become positive 2 if it's an ion. Nitrate's -1. So then your formula is going to have to be PbNO3 2. Okay, one more example, and then we're going to move on to the right side of the activity series and talk about that one. Okay, here's our next pair. This is rubidium and lithium dichromate. So rubidium is going to be metal A, and lithium is going to be our metal B. Okay, let's jump to our activity series and compare the positions of rubidium and lithium. Okay, here's rubidium. Rubidium is metal A. Here's lithium. Lithium is metal B. So Rb is lower than lithium this time. So Rb is less active than lithium. So that means that Rb will be unable, Rb cannot take the place of lithium. It can't knock lithium out and bond with the dichromate. So we're going to write no reaction. Okay, let's go back to the activity series for a moment. You'll notice that the right-hand side lists 4 members of the halogen family. Halogens, in this case, can also undergo single displacement reactions. Halogens can try to replace a different halogen. So you would have the halogen, the free halogen, trying to become, in this case, a negative ion, an anion, and not a cation. It's very important that you know that halogens will only replace other halogens. So you can only compare the activity of elements that are in the same column. You can't say, is strontium more active than chlorine? And strontium and chlorine, they are not competing with each other, okay, because that's kind of what is going on. The metals are competing with each other for electrons. Instead, you know, strontium and chlorine would end up bonding together. So you can only compare 2 elements in the same column with each other to see if one could knock the other one out. So let's look at a quick example of what it looks like when we going to try to compare how halogens try to knock out other halogens. Okay, now do not forget that in this case the halogen elements are always going to start out diatomic. Okay, in this case, if you look very carefully, here's one halogen, here's the other halogen. So here's our elements A and our elements B. Okay, now the halogen's in the second position. So now we're going to compare the activity of fluorine versus the activity of chlorine on the activity series. Okay, so we go to our activity series, and fluorine is higher up than chlorine, so fluorine will be able to knock out or replace chlorine. So that means that the chlorine will get kicked out, and the chlorine will go back to being a diatomic element. And the magnesium and the fluorine will bond together. Now remember what I told you, you have to check oxidation states. That always happens in every compound. I don't care whether it's metal-metal or halogen-halogen in your activity series. Okay, magnesium is going to be +2 and chlorine is going to be -1. So magnesium will still be +2. Now you have fluorine as an ion. Fluorine is -1. So that means it's MgF2. Okay, let's do another example. Let's look at bromine. Here, bromine is diatomic. And aluminum iodide. Okay, bromine here is A. Iodine is B. Go back up to our activity series. We're trying to see if bromine is capable of replacing iodine. Okay, bromine is higher than iodine in this little short list, so bromine will be able to kick out and take the place of iodine. So the iodine will get kicked out, and the iodine will return to its diatomic state, because it'll be a lonely metal, a lonely nonmetal. And now the aluminum and the bromine are going to bond together. Okay, aluminum is always +3. In this case, the iodine was -1. Now it's aluminum +3 and bromine -1. So it'll be AlBr3. This is a really important step. Okay, don't skip this step or you'll end up with an incorrect formula here. Okay, one last example before we wrap up here. Let's have iodine and sodium fluoride. Okay, iodine is element A, and fluorine is element B. So we're going to compare iodine and fluorine. Look at our activity series. Iodine to fluorine. Iodine is lower than fluorine, so iodine will be unable to make the change. So that means that we will write no reaction. Okay, so just remember that when you do single displacement reactions, you need to use your activity series to guide you. When you're writing these new products, do not forget to always write in your new compound the positive ion, then the negative ion. For example, if I wrote this as SO4K2, that is incorrect. The positive ion always appears first in any ionic compound.